Hello guys, today I'm going to show a simple proof. This is for like a real analysis 1 course. Basically the theorem states that every sequence has at most one limit. It's a pretty basic and simple proof. So first, just to get like an intuition, for example, if we imagine a graph where here we have the natural numbers and here we have this goes like 1, 2, to like infinity, and here we have the value of our sequence, so I guess an. So for example, if our sequence was the 1 over n, if our sequence was the square root of x, for example, the values would get, like slowly bigger and bigger, they grow to infinity. But imagine we have a sequence like this, some sort of sequence, but it has a limit. And let's say we can like say that the limit is over here, and we can call the limit of the sequence L1. So eventually, as n goes to infinity, all the terms of our sequence are gonna, converge to L1, and at infinity, our sequence will equal this value. And now we can imagine that this sequence has another limit, which is going to be a bit higher up, and we can call this limit L2. So basically, we can say our sequence has two limits, L1 and L2, and then we're going to show with the definition of a sequence of with the definition of like a limit of a sequence, that this is impossible. So basically, we know if L1 is a limit, then we know that for every epsilon greater than 0, okay, actually first I can just show you what's even going to happen in the proof. Basically, we're going to choose an epsilon ring, basically like around these two limits. So we can have a little ring over here, so like this and like this. And basically the size of this little area can be epsilon and epsilon. And basically we're going to show that, since with the definition of a limit, we have to have infinitely many terms inside this belt, inside this area. If L1 is truly a limit of a sequence, then it's impossible to have any points in this area because these two belts are not touching. So basically that's kind of going to be what we're going to try to show. So basically, for these two belts not to be touching, we know that the distance here is d, and the distance is just L2 minus L1. And so basically we have to choose an epsilon which is smaller than L2 minus L1 over 2. Basically that means that like these two epsilons here won't be touching. There's always going to be a nice little gap here. And basically with that choice of epsilon, so I don't know, we can choose L2 minus L1 over 3, for example. That can be our epsilon. And basically now with the definition of a limit, we know that for every epsilon greater than 0, for example, for this one that we choose, there exists an n from the natural numbers, where for every n greater than that n, the difference an minus L1 is less than epsilon. And so L1 is our limit here, an is just, the terms of our sequence. For example, if n is 1000, then every an, for example, the 1001st term, the 1002nd term, the 1003rd term, all of these terms, if you subtract them from the limit, it's going to be less than epsilon. Basically, that's true. If L1 is a sequence, this holds. That's the classic definition. But we also know that for the same epsilon, for example, for every epsilon greater than 0, and we choose the same epsilon now, there exists, and this is n1 technically, because this n, depends on your limit. And now for the second limit, there exists an n2 in the natural numbers, where for every n greater than n2, we're going to mark this n1, we have that an minus L2 is less than epsilon. These are just the two definitions of a limit. And if both of these are limits, then these two definitions have to hold. So basically, now the trick is kind of that we choose an n. We can choose an n, like, I don't know, let's call it n0, which is going to be the maximum between n1 and n2. So it's going to be the largest value. Then we can also choose n0 plus 1. So basically with that, we know that n0 plus 1, and we can just, name that n. We know that this n is greater than n1 and it's greater than n2. And basically what this allows us to do is that we can now, since we pick that n, if we choose an an term, if our term an is greater than this n, we know that an minus L1 is less than epsilon, because obviously, this n, which is, the same as this one, is greater than n1, so we know that this holds. But we also know this n is greater than n2. This also holds. So we also know that an minus L2 is also less than epsilon. Both of these things have to hold. And now we're going to see how a contradiction arises from this. Basically, here we can rearrange this to say that an is less than epsilon plus L1. And here, since there's an absolute value here, we can times this expression by -1. So we get minus an and plus L2. Doesn't matter, it's an absolute value anyways, the difference doesn't matter. I mean, we just want to know like the difference, you know, the sign doesn't matter, we can take the absolute value. So basically we can say that an is greater than L2 minus epsilon, just, you know, putting an on the other side and subtracting this. And basically we get these two terms. So basically now if we put this together, we can see that we get L2 minus epsilon is less than an, which is less than epsilon plus L1. And basically with that, we get that L2 minus epsilon is less than epsilon plus L1. Now we can put epsilon on the other side, so we get that L2 minus L1 is less than 2 epsilon. And here, for example, I mean, first of all, just looking at this like intuitively, since epsilon is any arbitrary number greater than 0, this can basically become infinitely small. And if we say the distance between L2 minus L1 is, for example, d, we can just choose an epsilon value, you know, it doesn't matter what epsilon value we can choose. We can choose epsilon equals d over 10, and, you know, so this difference will be smaller than d. So basically, whatever real number we choose, whatever number we choose, basically L2 minus L1 will always be, the difference between these two can always be less than that number, because we can choose the epsilon infinitely small. So basically the difference can't be anything else but 0. So no matter how small the difference we choose, we can always choose an epsilon smaller. So that already kind of proves it for us. But let's say, you know, we said that epsilon equals, in our example, we said epsilon equals L2 minus L1 over 3. So we can say L2 minus L1 is less than 2 times L2 minus L1 over 3. So basically, if we, you know, mark L2 minus L1 as like A, we get that A is less than 2/3 A, which of course doesn't make sense, you know. This is, you know, 3A is less than 2A. This is a contradiction. So, you know, if we say this has to be true, we obviously get to a contradiction, which just shows us that, you know, you can't have more than one limit. You can only have one limit in a sequence, and you can see it with this contradiction, or just, you know, with the logic that epsilon can be infinitely small. So no matter what the difference between L2 and L1 is, you can always find an epsilon smaller. So basically L2 has to equal L1, and this shows the uniqueness of the limit. Every sequence can only have one limit. It's a pretty basic proof, but it's pretty nice also to see the geometric intuition here. Kind of makes more sense. And all you need to know is basically just the definition of a limit of a sequence, and you just, you know, apply it for both these values. And yeah, it's a pretty basic proof in analysis 1. Hope that helps. First video, let's go. Yeah, thank you for watching.